Hello students, today we are going to start the second part of refraction at plane surfaces. In our previous class, we have discussed about the refraction at various surfaces, that is the laws of refraction and the on which this Snell's law, that is mu, depends. We have discussed that. Today we are going to start refraction at plane surfaces. Now the topic is refraction of light through a rectangular glass slab. What will happen when a light ray pass from a rectangular glass slab? In a rectangular glass slab, we know that the upper surface and the lower surface are parallel. Like that, if we take a rectangular glass slab like that, this is the rectangular glass slab PQRS, if I name it PQRS. Now a light ray is incident obliquely on the upper surface of that rectangular glass slab. Okay, look at here, this is a glass slab and this is the air medium. This is the air medium, this is the glass medium. Now if a light ray coming from a rarer medium to denser medium, it will come towards the normal. Like that, if I draw here a normal, then this ray will come towards the normal, that is it will come in this direction and strikes at the lower surface. Okay, making an angle of incidence here I. This is the angle of incidence I, angle of refraction R. Now look at here, this ray incident or strikes at the lower surface of the rectangular glass slab. After coming out, what will happen? Look at here, this is a glass, this is glass, air, this is also air. Now the light rays are coming out from glass to the air, that is from denser medium to the rarer medium. If the light rays are coming out from denser to rarer medium, it will move away from the normal. If I draw here normal, then it will move away from the normal. It will move away from the normal, as this is parallel to each other, that is this normal and this normal are parallel to each other, that is why it will also R. Okay, and this angle is called the emergence angle, and this ray is the emergent ray. So one thing is that after observation we will find that this ray and this ray, that is the incident ray and the emergent rays, are parallel to each other. Now one thing is that if we extend this ray in dotted line, we will get like this line. Okay, now what is going on here? If there is no rectangular glass slab, then the light will passing directly in this direction. Okay, but as the rectangular slab is in front of that light, that is why the ray is coming out in this direction after refraction. Okay, now there is the perpendicular distance. If I draw here the perpendicular distance between these two rays, that is the incident ray and the emergent ray, is this. Okay, I denote it by x. This distance, this perpendicular distance is known as the lateral displacement, that is the perpendicular distance between the path of emergent ray and the direction of incident ray. Okay, the direction of incident ray and the direction of emergent ray. This perpendicular distance is known as lateral displacement and it is denoted by x. Now this lateral displacement depends on some factors. First is this lateral displacement depends on the thickness of that glass. rectangular glass slab. Okay, this thickness, if I denote it by T, then it depends on the thickness of the glass plate. Okay, so more the thickness of the glass, more the lateral displacement. Next one is the angle of incidence. More the angle of incidence, more the lateral displacement. Third one, the refractive index of the glass. Okay, the refractive index of the glass. This lateral displacement also depends upon the refractive index, that is the medium, that is the denser medium. More the refractive index of the glass slab, more the lateral displacement. Okay, this is the refraction at parallel glass slab. The next one is the refraction through a prism. What will happen if the light rays are incident on the refracting surfaces of the prism? What will happen to the emergent ray? Now we are going to discuss this portion. Now at first, prism. What is a prism? A prism is a transparent media bounded by a 5 plane surfaces with a triangular cross sectional area. Okay, triangular cross sectional area. Look at here, I am trying to draw a prism with 5 surfaces. Look at here, this is a prism, this is a prism, okay, this is a prism. Look at here, there are 5 surfaces here. These 2 surfaces, that is this surface and this surface, these surfaces are the refracting surfaces, and this angle is called the angle of prism. Angle of prism. These are the refracting surfaces. Refracting surfaces. This and this. These are the refracting surfaces. Now this is the base, and this base is always grounded, or it is always rough. Okay, these are the rough surface. Okay, now discuss about the thing. What will happen if the light rays are incident on that refracting surface, and the angle of deviation. We will discuss the angle of deviation. Okay. Sorry, I am drawing a prism. This is a prism A, B, C. A light ray incident obliquely on the refracting surface of a prism. After incident on that refracting surface, when it pass through the glass of the prism, that is inside the prism, as this is the air and this is glass, that is it is the rarer medium, this is the denser medium. Now when light rays are falling from rarer medium to the denser medium, it will bend towards the normal. I am drawing here a normal. Okay, it will bend towards the normal. Like that, it will move in this direction if there is no prism. Okay, this is the actual path of that incident light, in this way. Now I am O, P, and this is Q. The light incident strike at the second refracting surface. After emergent through the prism, it will bend towards the, it will bend away from the normal. Why? Because this is the denser medium and this is the air, because this is a rarer medium. After emergent through that surface, it will move away from the normal. Okay, look at here, look at here. At first I am extending this emergent ray and it strikes at point M, so that we can say that this emergent ray is coming out from point M. This is appears to coming out from the point M. Okay, now this is the incident angle I, and this is the angle of refraction, and I am denoting it by R1, and as this is the angle of deviation for this ray, and I am denoting it by Kronecker delta 1, and this is the angle of incidence in the prism, and this is the angle of deviation for this ray. Now actually the angle of deviation for this prism is this, because the actual path of the ray is along this line, and the emergent ray appears to coming out from the point M. That is why this is the angle of deviation for this prism, and it is denoted by Kronecker delta. Okay, Kronecker delta. Now I am going to calculate the angle of deviation delta. Look at here. This is the triangle PMQ, and we know that the external angle is equal to the addition of two opposite internal angles, like that. If this is a triangle and this is the external angle, this external angle will be equal to the sum of these two angles. Okay, similarly from this triangle PMQ we can write that the external angle is here delta. Okay, so delta is equal to delta 1 plus delta 2, delta 1 plus delta 2, and as it is the summation of the two opposite internal angles. Okay, now at this point, when the incident ray strikes at point P, we will say that I is equal to delta 1 plus, sorry, this is I1 according to your book, this is I1, and I am writing this emergent angle I2. Okay, you can change it as you wish. Okay, I1 and I2. From this point we can say that I1 is equal to delta 1 plus R1. Okay, delta 1 plus R1 is equal to I1. From this we can say that delta 1 is equal to I1 minus R1. Similarly from this point Q, when the ray strikes at point Q, we can say that delta 2 plus R2 is equal to I2. Delta 2 plus I2 is equal to R2. Therefore delta 2 is equal to R2. Look at here, I made the mistake here. This is delta 2 and this is R2. R2 is equal to I2. So delta 2 is equal to I2 minus R2. Put the values on this equation. We will get delta is equal to I1 minus R1 plus I2 minus R2. I2 minus R2. I1 plus I2 minus R1 plus R2. This is equation number 1. This is the equation number 1. Now, from this quadrilateral M, P, N, Q, from this quadrilateral M, P, N, Q, we can write that the summation of the four internal angles is equal to 360 degree. Okay, 360 degree, that is angle PAQ plus angle APN plus this angle PNQ and this angle NQA. This is equal to 360 degree because all the internal summation of the all internal angles always 360 degree, but this is the normal. So we can say that this angle is P angle and the Q angles are 90 degree. Each of these angles are 90 degree because we draw here the normal. So we can say that this angle and this angle is 90 degree. So I can write that PAQ plus PNQ is equal to 360 minus 180 degree equal to 180 degree. Look at here, I am denoting it this angle A and this angle N equal to 180 degree for my simplicity. Okay, next one, this is the triangle PNQ and the summation of the all angle of a triangle is 180 degree. I can write that from this triangle PNQ, we can say that R1 plus R2 plus N, angle N is equal to 180 degree. 180 degree. Now the value of N I am calculating from here. N is equal to 180 degree minus angle A. Put the value of A here. R1 plus R2 plus 180 degree minus A equal to 180 degree. Okay, 180 180 cancel out. I can write that angle A is equal to R1 plus R2. R1 plus R2. So from this equation 1, I can say that delta is equal to I1 plus I2 minus A, where A is the angle of prism. So from this Kronecker delta, we can say that this is the angle of deviation for a prism. Okay, for a prism, this is the angle of deviation. Look at this equation, delta is equal to I1 plus I2 minus A, where I1 is the incident angle, I2 is the emergent angle, and the angle A is equal to the angle of the prism. So this angle of deviation depends upon some factors. First thing is that it depends on the angle of incidence. Second is the material of the prism, that is depends on the refractive index mu. Third one is the angle of the prism, and it depends also the wavelength of the light we used. Okay, wavelength of the light we used. Now when the angle of incidence increased, when the angle of incidence is increased, then the deviation at first decreasing slowly. After a certain time, after a certain increasation of this angle, it will be increased. So if we plot the graph delta along y-axis and angle of incidence I along x-axis, then we will get at first it is decreasing. After a certain increasation of angle, it will be increased. So for this angle, the angle of deviation is minimum. In any experiment, we can say that for minimum deviation, I1 is equal to I2, and I am writing here I1 is equal to I2 is equal to I. Put the values here. So we will get delta minimum, that is the minimum angle of deviation. So I1, that is I plus I minus A. Okay, so 2I minus A, this is the minimum deviation. Now the second portion is the mu, refractive index of the medium. So it is found that for a given angle of incidence, the prism with a higher refractive index produces so greater deviation, and it is also depends on the angle of deviation. Okay, it is also depends on the angle of the prism. Now the angle of the prism is A. If the angle of the prism increases, the angle of deviation will also be increased. And the last portion, the wavelength. When the wavelength of the light which we used for this calculation, that is the monochromatic light, single color light, the angle of deviation decreases with the increase of the wavelength of the light. Okay, so these factors affect the deviation, that is the angle of incidence, refractive index, third one is the wavelength, and the fourth is the angle of the prism. These are the factors which affect the deviation. Okay, that's all for today's class. Next day we will discuss the next portion of refraction at the plane surfaces. Thank you.